Tonight we're looking at variables. Variables is the first part, and then we will be talking about conditionals, where we're making the computer have to think. But variables are a really key concept in programming. That means we can make an indirect reference to a value. We can store a value. We can have access to something without having to necessarily know what its value is. We can just say, hey, I want the name of this. I want to know this number that is represented as, the score in my game, or the position of my object. I want to know where that object is, but I don't want to have to write that number down every time. I just want to have a reference to it. And a variable is really about making a reference to a value. Sometimes the reference is referred to as a variable is a container. It's a box that we store this value in. And that's kind of a true assessment. So we can think of, in this case, I say x is equal to 100. So x is going to be a number, happens to be an integer, meaning it's a whole number. It's not fractional. It's not like 10.1, 10.34. It's 100. There's nothing, no decimal point, nothing after it. And we say x is equal to 100. So that means I'm now storing the number 100 in my variable, which is x. One thing that's required when we are creating or making variables and processing is we have to tell the computer ahead of time what kind of piece of data are we trying to store. Is it a number? Is it a letter? Is it a word? Is it an image? Is it an object? Is it something? But the computer needs to know what kind of object it is, because it needs to know how much memory it needs to set aside to keep track of that piece of information. So some languages, we just use the word var, short for variable, VAR, and then we just list the name and then we say what the value is. Other languages require us to use a specific data type. We have to say, is it an integer? Is it a float? Is it a string? Is it a Boolean? These are all data types. They're kinds of information that we're keeping track of. So integers are whole numbers, positive or negative, including 0. A float is going to be a number that can have something after a decimal point, but it doesn't have to. If we're keeping track of something and we know we don't always get a whole number or need a whole number, sometimes I may want the fractional number with a decimal, then we need to use float. And that refers to, then we have this floating point and then the numbers occurring after it. So technically float, where I say 1, that would be like 1.0000. It's still 1, but it gives me the option of putting the zeros after it. If I said int ellipse width equals 1, I would not be allowed to have the zeros. I can't have a decimal point. I can't have anything after it. I'm stuck with that whole number. So integers are whole numbers. Floats are numbers with decimal points. And then you will notice we have string, which is referring to a collection of letters. We have a character data type, which can be then a single character, and a string, which can be one or more letters. Most of the time, we use string as our designation when we are talking about letters. We can use character, but string is the preferred because it gives us the option to have one or more. The reason you would use character over string is because character would then take up a little bit less memory. And if you're at the point that you're so concerned about performance, the differences and nuances between string and character would be something that you would have addressed by that point or in other ways in your program. But 99.99% of the time, if you are trying to make a variable referencing letters or a single letter, you will use a string. One key important thing to notice is that unlike the other data types, string has a capital S on it. So you will see that there's the capital in the word string, And that is because string is not actually a primitive data type like integer or float or Boolean, but it is now actually the string object or string class, which is related to the character, but it now, when something is a string, it actually has a series of methods or properties that we have access to. It's not just letters. So think of it as complex. The fact that we can see it has words, different letters, we can put extra special characters in like the /n. It means it has power. And because of that, it gets a capital. And if you don't want to remember anything else, just remember string is always capitalized. The other data types are lowercase. And just live with that and accept that is how our grammar, our syntax is required when we're working with this. A Boolean is a data type that has one of two values. It is allowed to be true or false, not both. It can't be ambiguous. And it's allowed to flip-flop. Now, if you think about a Boolean has values of true and false, black, white, 1, 0. If we think about how our computers think in terms of on, off, 1, 0. So binary computer code is just a series of zeros and ones. Your computer processes everything at its barest level through a whole series of Booleans. Something is on or something is off, and that is it. So a Boolean is an extremely powerful data type that we can use extensively when we're doing our programming, because we're continually checking for whether something is true or whether something is false. We're trying to ascertain that value, and in doing so, we're able to do something with it. So int, float, string, Boolean, the four most common data types that you will use regularly in the programming that you're going to do. Now, working with this, we'll see box size starts out at 1. I'm going to work with the box first right now. So I've commented everything except box size equals mouse y. And I'm drawing a rectangle at x and y, and then box size, comma, box size. So its height and width are based on box size. Box size is related to the y of the mouse position, and I will uncomment out where it will now print out at the bottom of the screen what the mouse y is, so we can see how that's interacting. So we did a little bit of this last time where we used the mouse x, mouse y. So we can see as I move based on the y value, my box is changing size. So if my y is at 1, it's a tiny little square, and then we can grow it up to, say, 100. So now I have a box that's at about 104 by 104 pixels in size. So we can see the box is responding to this mouse y value. Mouse y is something that the program is keeping track of. We have mouse x, mouse y, p mouse x, p mouse y. That is what the value was on the previous frame. So these are values that we can use for animation or interactivity as we see fit. But instead of doing that, I'm going to modify mouse y so it changes over time. Or I mean box size. So box size is now going to change over time. So box size is now going to increase. So what's going to happen is the first time I go through, box size will be 1. Then box size will be 2. Then box size will be 3. Because box size is being set equal to box size, whatever it was, plus 1. That's what this line of code says. So I'm going to even print out a statement for that. So we can see how that is occurring. Comment that one out. So box size will increase. We'll print it out, and then we will draw a rectangle based on box size. Again, at x and y, and we can see x and y are 100 and 200 respectively. When it comes up, we can see it's automatically increasing and going and growing and growing and growing and growing. So each frame that my project ran, box size increased in value. And as box size increased in value, it kept redrawing it. So what's happening here is box size is a value. It's a number. That number's changing. But at the end of the day, I don't even really care what it currently is. I just know that I wanted it to change to cause that animated effect, to cause that visual movement on screen. And that's where a lot of the power of variables comes in, is that one, we can kind of store a pathway to access a value. So we can have that value. You can think of it as in a box, or it's a value that we're reaching out and grabbing a hold of and saying, hey, I want you. I don't care what you are, I just know I want you. But we can also take that value and manipulate it and modify it on a consistent and regular basis. And that's how a lot of fun can start to occur with our values. Now, so with the ellipse only being a tiny little speck, we're going to need to modify ellipse width and ellipse height so it can start growing. And it's possible that we can add to ellipse height and width just like the box. So I can look at it and see that it starts growing. Oh, I'm only modifying the width there. Whoops. I'm going to stop the box. We don't need that box growing anymore. So we'll get rid of all the boxes. Now, right now the width and height of the ellipse are being modified on a per frame basis. So if we watch this happen,
Is that a times? That star? Okay. Multiplication, sorry.
so we can see that the ellipse is growing in a linear manner horizontally, but it's growing in a much slower and then more dramatic fashion as the value gets multiplied, because we're multiplying the value using the star sign as multiply, plus for plus, star for multiply, 1.01. And I mean, if we want it to happen a little bit faster, I could even change something to, I'll just multiply it by 1.5, and I will even add 1.5 so we can see the difference between add and multiply and run it. And we should see a noticeable change in the height until it went so fast it just disappeared off screen. Became an impossible value too quickly. That's why previously it was 1.01, so it's at least slow enough so we can see something occurring on screen before it blows up. So we can see that once the multiply takes off, it goes at a fairly dramatic fashion. So we can multiply values, we can add values together to our values as we're working with them. So variables can be modified or changed or updated on a per frame basis. So we take the width and we set it equal to whatever it previously was plus whatever value we wish to add to it or multiply that value by. So that is how we are able to change a variable amount. So we can add something, multiply something, divide something, subtract something. All of our basic math operations can be applied to a number-based variable. So currently I'm drawing my ellipse at this x and y location, and I'm applying ellipse width and ellipse height to those values. Now, instead of just blindly changing them forever, what I'm going to be doing is using a conditional statement. A conditional statement is where I say, hey, if something is true, then do something. That's all it is. If something is true, do something. And then we can even have else ifs and elses and all of that, and we'll get into that in a minute. So what I am asking the computer, I'm saying, hey, if the width of the ellipse, that value, is less than 200, then I want you to start, increase it by 1 and increase the height multiplied by 1.01 like what we saw before. But I can say if the ellipse width is greater than 300, so that means it kept going until it hit, so after it hit 200, all right, if the ellipse width is less than now 300, so once it gets up past 200, then it's going to kick into the 300. Then it's going to start increasing size and height much faster. And once it's gone beyond 300, what's going to happen is it will now choose a random color to fill my ellipse, and then it causes the seizure strobing effect. So what we will see is the ellipse, while it's growing until it hits a width of 200, it will grow the same as what we saw before. Then it's going to instead of growing more horizontally, it will suddenly grow very fast vertically. And then as it does that, once it hits 300, then it goes into the strobing Easter egg. So to watch this happen, we see it grow horizontally, and at 200, it will start growing vertically into an Easter egg, and then it will start strobing when its width hit 300. So what we're doing is we're creating a situation where we are checking for a condition. That's why an if-else statement is referred to as a conditional in programming. So we're looking for a condition. And when that condition occurs, we do something. And if that's not happening, then we can say, well, else if, how about this other condition? And we can have as many else ifs as we want. And when all of those have been exhausted, we can even have an else statement that would be, so if that's no longer true and if that's no longer true, well, then let's just go do this final thing, which is where I choose a random color which causes the strobing effect. Working with the movement file, I have 4 floating variables, x, y, width, and height. Then I'll have speed, y, and gravity that we will be adding into the fun mix momentarily. Create a document 500 by 500. Set x and y initially to the middle of the screen at 250 each. Width and height for my little box will be 20. And then speed and gravity we will be worrying about in a little bit. Then I'm going to draw my color out my background, set the fill color to red, draw my rectangle, run, and when it comes up we will see I get a red box. It does not animate, does not move, does not do anything because none of my variables, none of the values associated with this object are changing. Now one thing that we can do is we can now change the position of this object if we think about adding in a speed value. Now normally with objects we could just use a single speed value, but if we get more technical, are we moving a speed horizontally or a speed vertically? If we just say speed, which one does it refer to? And that is why I elected to use a speed y variable. Speed y referencing I'm going to make my object move in a vertical fashion. Now speed y starts out at 5. So what I am going to do is I am going to modify the y position of my object by 5 pixels every frame. So initially my object will start out at a position of 250. Then the next frame y will be equal to 250 plus speed y, which is 5, so it becomes 255. So it will now draw the box 5 pixels lower. The next frame, 5 pixels lower. The next frame, 5 pixels lower from where it was previously. So as we do this, we're modifying the position of the object. So when I run, I will watch my object fall. So the object falls by 5 pixels each frame. Watch it again because it's fun to watch things fall. And now it's falling into perpetuity. It's falling forever. So what would be nice right now is to say, well, hey, when that object hits the bottom of the screen, I want it to go back up. So if the y value becomes greater than 500, remembering that 500 is the size of our project, and I tweaked that a little bit so it doesn't go all the way down in because Rex draw, but we'll get rid of that for now. We'll add it back in. So I say if y is greater than 500, now got a curly brace there. And now what we're going to do is we want our speed to change from being a positive number to a negative number. And the way that we're able to do that, there's a really cool programming trick. If we have a number and it's a positive number, if we multiply it by -1, whatever that number is becomes a negative number. But what's even cooler and more exciting is when we have a negative number and then we multiply the negative number by -1, that negative number becomes a positive number. So we can actually now start to construct a scenario where we can hit the bottom, bounce up, hit the top, bounce back down, and we're going to be able to create this permanent bouncing, annoying situation. And we will get to work with that in just a moment here. By inverting our speed, so we invert the speed if we take the speed and just times it by -1. Knowing that that changes whatever is positive to negative, and if it's negative, it becomes a positive value. But first, we're just going to bounce off the bottom. So when I run it and do that, we see it hits the bottom and goes up and up and up and up. So now we need a speed limit at the top, because currently I have the speed limit at the bottom. I hit the bottom, but I'm going to run it again because there was one little issue with that. And if you notice that when it hit the bottom, it went all the way off screen, and then it started going back up. It's going, in fact, 20 pixels too low. And that's because rectangles draw from their top left corner. So because it's drawing from its top corner, that means when we're checking for X, it's when that top left corner got all the way off screen that it said, oh, hey, wait, whoa, I'm too low. Now I need to invert. And that's why in the original code that we started with, it had a -h, or the height of the object. So if I go and change the height of my box to 30 or 40, my code still works. Otherwise, we could have just typed in a number like 480, which would have worked. But we want something that gives us more flexibility down the road. Now, watching this, we will see that our box hits the bottom and immediately bounces back up and then keeps on going forever, because there's no check. There's no time where we're checking for the top. That's what we will uncomment in just a second. Adding in so we have a top limit, because otherwise it seems kind of silly when it goes all the way off screen. Then we can invert when it also hits the top. So we say else if y is less than 0. So that means the object has tried to run itself off screen. At this point, we can see that we now have an object that is perennially hits the bottom, hits the top, and it will just keep on going forever. There's no change in speed, no degradation of speed, no anything. It's just bouncing permanently up and down, up and down.